we get new results almost every day. We've been trying.
I've been hearing about it almost every day.
Yeah, we've been trying to release as many as we can, as fast as we can.
Okay.
Yeah, and we're also well on our way to completing our next mission, the Roman telescope.
The Roman, no, okay.
Yeah, which is scheduled to launch next year.
Oh, launch, okay. On time?
Before time, actually. The schedule is 27, but we are hoping to launch it in 26.
Oh, that's fast.
Yeah.
And Mr. Hubble?
Mr. Hubble is going strong so far.
That's, I mean, Hubble and the two Voyagers are real good stalwarts.
Yes, and the solar probe is also.
Yeah, solar probe, yeah. Okay. We wait for a bit more for Prof. Kraus to come in. I still don't see him in. Prof. Dawson, if you don't mind, you want to switch on your video? Oh, okay. Oh, we can't hear you. You're muted.
Yes, I am
Okay,
there.
right, nice. Okay. Where are you?
São Paulo, Brazil.
Oh, in Brazil.
I am in Brazil now.
Okay. Wow, that's direct 12 hours across from us.
Yeah, almost 9:30 p.m.
PM, yeah. We are and almost 12 hours plus one, yeah. Okay. Nice to have you. Have you met Prof. Dr. Hashima?
No. Hello. Nice to meet you.
Nice to meet you. Come to Washington, D.C.
Okay.
Yeah.
Prof. Kraus is missing.
You know that I did a postdoc in Maryland, at the University of Maryland, many years ago.
Oh,
so I used to live in Greenbelt.
I'm not actually in Greenbelt. I'm at headquarters, which is in D.C.
Okay. Now, I also read the recent news about the observatory in Chile and the
All right. Good evening, Prof. Kraus. Nice to have you back.
To be back. Hi.
Okay.
Just gonna close the door here.
Nice hairstyle too.
It's late at night where I am. Hold on. Okay. Here we go.
Okay. Since all three are here, I will kick off with introductions and we'll move on from there. Okay?
Great.
Okay. Salam sejahtera, selamat pagi, and a very good morning to all gathered here virtually. We are here for International STEM and Innovation Colloquia, Series 23, Special Dialogue Series 1. Thank you to Drs. Nazri Halif and Sharifah Nur Faiza, as well as UNIMEP Vice Chancellor Prof. Zaliman Sauli and Deputy Vice Chancellor Research and Innovation Prof. Rizal Fandi, their respective officers, and broadcast control team here led by Mr. Shahrizan for hosting this event. I'm Prabha, the moderator for this Isaac's special dialogue series on why basic science still matters, the hidden engine behind every breakthrough. Before we begin, as normal, I would like to very briefly introduce our esteemed speakers for this dialogue series 1. Prof. Kraus, our series 19, October 24 speaker, and also president of the Origin Project Foundation USA. Dr. Hashima Hassan, our series 4, March 2022 speaker, as well as program scientist and the education outreach lead for astrophysics, NASA USA. And I must mention, an ardent supporter of our Isaac series. And lastly, a very warm welcome to Prof. Sylvina Dawson, President of the International Union of Pure and Applied Physics, Geneva, Switzerland, but she's in Brazil right now. Okay, we wish our distinguished panelists a very good evening. Our panelists will share with us on why basic science still matters, the hidden engine behind every breakthrough. If anyone wishes to ask anything, hope you can wait till the end of our dialogue, or it'll be better if you could type it into the chat box. Thank you, guys. Before we begin, could our panelists please introduce your good selves and what do you do? Prof. Kraus?
Okay, hi, I'm Lawrence Krauss, and I'm a theoretical physicist, and whose research work has spanned the intersection largely between two areas of fundamental physics: elementary particle physics and cosmology, from the very smallest structures in the universe to the very largest. And what's wonderful is there's an intimate connection between those two things. And so that's my research, but I've also spent a large part of my career on trying to connect with the public and motivate them and excite them about the fundamental wonder of our universe through my writing in books and my appearances on television and other things. And so I guess that's all I need to say. Well, no, let's say one other thing. After my retirement, I created a foundation called the Origins Project Foundation, which does a number of things to continue the interaction with the public, and among other things, right now, a podcast that brings in scientists and non-scientists for in-depth discussions about the most important ideas in the 21st century. That's all I'll say.
Thank you, Prof. Kraus. Dr. Hashima?
So I'm Hashma Hassan. I also actually started my career as a theoretical physicist. I got my degree in theoretical nuclear physics from the University of Oxford. But for the last 30 years, I've been working at NASA headquarters as a program scientist, where I've led, by now I've led about 13 missions spanning the wavelength, right from Gravity Probe B to flagship missions, Hubble, Hubble, Sophia, James Webb, and now I'm at the other end of the spectrum with New Star and XP, which are X-ray missions. And I'm also the lead for education and public outreach for astrophysics, and I'm really passionate about that and about bringing science to the public and to students.
Nice. Thanks, Dr. Hashima. Dr. Dawson, Prof. Dawson.
Okay, thank you. My name is Sylvina Ponce Dawson. I am a physicist from Argentina. I am a professor and researcher at the University of Buenos Aires, currently on sabbatical in Sao Paulo at the Center for Theoretical Physics there. My research is in biological physics and nonlinear dynamics. And currently I am the president of the International Union of Pure and Applied Physics, which is the only international scientific union that covers all areas of physics. We have about 60 territorial members, and we also have some corporate members. And one of the aims is to help solve the problems of humanity with the use of physics and promote international collaboration in physics. And my initial times with the IUPAP were related to gender in physics. and gender in science. So I have also a trajectory in trying to close the gender gap in science.
Okay, thank you, Prof. Dawson. Just a side question on that. Is physics dying? I see a lot of departments closing in a lot of universities.
Well, I don't think it is dying. Maybe it is transforming into something different.
Okay.
Well, we feel it's very much alive, though.
Okay.
So, and the training that physics gives to physicists allows them to approach lots of problems, because data science, let me tell you, there are lots of physicists working on that, and of course in other areas. So I don't think it is dying. Maybe it is transforming itself.
Okay.
Yeah, I
Nice.
think the
Thank you.
rumors of the death of physics are overblown. Physics is a
Pardon,
lot of.
pardon?
I said rumors of the death of physics are overblown. There's a lot of. There's some areas of physics that may be stalled, but there's a lot of areas in the universe where it's quite active, and as Professor Dawson just pointed out, that there's lots of new areas, including biology, where physics is becoming of more vital importance.
And I will add, as Silvina said, the training that you get as a physicist enables you to branch out in a lot of different fields, which is why I am now managing missions in astronomy, whereas my PhD was in nuclear physics.
Exactly. I've been a professor. I was a professor of astronomy for 30 some odd years, but I never took a course in astronomy in my life before that. And we also used to, I also used to tell people when I was chairman of a physics department, young students, that a lot of people don't know this, but um, many physicists are employed as engineers, and it's and what we I used to say about that is that engineers learn certain techniques, but physicists learn how to solve problems, and um, and that's a tool that is particularly useful. So many employers are very happy to have physicists, because you can learn things, you can learn the details of after you graduate, but the technique of solving problems and thinking about how to do that is a wonderful training that physics provides for almost any area.
The
And
critical,
oh, I'm sorry.
that's the critical thinking.
Yeah,
Yes.
exactly.
I was at the International Conference on Statistical Physics last week, and you can see the wide set of problems that physicists try to approach, and in particular in machine learning, using statistical physics to understand why the new neural networks work so well, and trying to make their algorithms more efficient through this analysis and tools that physics gives. And then you have many interdisciplinary subjects that are also
That's new. That's new.
looked at with the tools of physics. So
Physics into AI. Okay, that's a good one. Yeah. All right. Um, and I would like to pose an open question. We'll start with anyone. We associate applied science with engineering, with some difference, of course. However, how do we differentiate fundamental and basic science, or is there no difference?
Yeah, it's a good, I saw that question before and I wasn't quite sure I understood it, but I mean, it's semantics. I think there's obviously a very important connection between fundamental science and what you might call basic science. If I were going to say that the only difference is that I think of basic science being the kind of elementary aspects of physics, the fundamental parts of physics that we use in all of our more advanced studies in electromagnetism, etc. And fundamental science, I tend to think of as the effort to try and reach down to the those laws that underlie all of the phenomena we see. So fundamental science, I tend to think of as looking at the basic things that determine the origin of our universe, why there are four forces in nature, such. And I'd say for me, basic science is the basic aspects of physics, from electromagnetism to the way we treat problems, to classical mechanics and so on. And what's really important, and I certainly try when I was lecturing and in my public lectures, to show that there are intimate connections, that even at the forefront of science, you can connect it to basic physics that people learn in high school, that there's a fundamental connection between those two things, and you know, from understanding dark matter, etc. And I always try and make that connection, and maybe we'll talk about it more. Anyway, I'll let everyone else answer the question as well.
Yeah. Dr. Jima, your thoughts on it?
I think Dr. Krauss has expressed it really well, because when I read the question, when he said basic physics, I really thought of my high school physics. What are the laws of motion, motion, Newton's laws of motion. And then fundamental, you start thinking of the elementary particles and, what makes up nature, how things are joined together. So I think Dr. Krauss has expressed it really well, and I don't think I really can add any more to it.
Okay. And Prof. Dawson?
Well, I think that the main difference is the questions that lead the research, basically. I mean, when you think of basic science, it's because you're trying to understand the workings of the world, how nature works, basically. And so your motivation is curiosity. And then when doing that, you eventually you find answers that allow you to intervene into that natural world and build new technologies. And we are seeing now, this is the International Year of Quantum Science and Technology, and we are seeing the second quantum revolution that is being highlighted in this International Year, which actually is based on the ideas that the first researchers, the first people who thought about this quantum science, they were very motivated to try to understand some experiments, and then they found all these world of things that were so counterintuitive, and now all those ideas are being applied for this new quantum revolution that we think it's going to change completely all the world of communications with safer ways of communication, that is also going to change the ways in which we secure communications. And so that was not foreseen at the time that the fathers of quantum mechanics were trying to answer those basic questions that were motivated in curiosity and what the entanglement meant or the superposition. And suddenly this turned into this huge technology revolution. So it's the questions that you try to answer, but that once you advance with that, you are not limited to answer those questions based in curiosity.
Okay, that's quite deep there. It's quite quite convoluted on how things are related there. But would I be wrong to say that fundamental, basic, applied?
Yeah, but they go back and forth, let me tell you. Because also when you want to enter into these intricacies of how the nature works, you need new equipment, and that also foster the development of new technologies. So it's a feedback. So it's not so much layered, it's very much intertwined, I would say.
Yeah, I would definitely say it's not a hierarchy. If anything, I might put basic at the bottom at a vertex and have fundamental in one direction and applied in another, stemming both from the same center.
Okay, intertwined.
Yeah. Anyway, as I say, it's semantics. So.
Okay. Semantics. Okay, that's nice. Thank you, guys. The first question to Prof. Krauss. From your experience leading the Origin Project Foundation, what have you seen is the most effective way to engage the public and policymakers about the importance of basic science, especially in physics?
Well, of course, it's always hard to. I mean, I try a lot of different ways, which is one thing. Not any one way engages every person. So one tries different things. Different people get excited by different approaches. But one of the ways I think I have that it is useful is it relates to what we just talked about, is connecting forefront science to really basic fundamental things that people might remember in high school. For example, in my book, The Physics of Climate Change, I tried to show that, a lot of people think of, climate change science is sort of, very complicated, and who knows if it's real science, and it's people attack it for a lot of reasons, and it involves complicated computer models, and maybe they're wrong, etc. But what I tried to show is that basic fundamental thermodynamics discovered hundreds of years ago, the basic things you can remember again from high school, or at least if you're not in the States, from high school, the apply, and you can understand. You can basically get much of what comes out of climate science from some very basic science having to do with thermodynamics, and that anyone can understand. Now, the details of what happens in Europe versus South America are complicated. Those require computer models, but knowing generally what's happening on Earth, um, you don't need to do that. Also, people get intimidated by.
Departments closing in a lot of universities.
Hello, I can't.
I don't think it is dying. Maybe it is transforming into something different.
Okay.
But we feel it's very much alive, though. So,
Oh, okay. I
and
couldn't.
the training that physicists give to physicists allows to.
Oh,
Okay.
I'm sorry about that. That was
It's all right. It's all right. And what I was going to say is that it also intimidates, the complex physics at the forefront also intimidates people. So when I'm talking about dark matter or the evolution of the universe, once again, I try and relate it to some science that everyone understands. So people can see that there is this connection, that there's intuitive understanding that makes sense. It's not some stuff we just invent so we can be supported, and that has nothing to do with anything that anyone is interested in. So I think that's, from my experience, a good way to cut through either indifference or fear or intimidation, or antagonism. Once again, especially in climate science, there's a lot of antagonism. But if you can, I try and show that at least that, let's forget all the details of what you need to do in the future, but let's just talk about some fundamental science. So anyway, it's that connection between forefront and basic, which I talked about earlier, that I think is probably one of the most effective ways to engage. And often there's well-known pedagogy that says that the only way people remember something is by confronting their own misconceptions. And people have a lot of misconceptions about science. I remember once giving a lecture for many of the leaders of the free world at a meeting where very many distinguished politicians, etc., were there, and I just, I asked people, if I drop a book and a piece of paper, which will hit the ground first, and everyone said the book, and then I said why, and of course half the people said because it's heavier, and then I just crunched up the paper and dropped the book, a standard thing that many physics professors do in a class, and they felt the same time, and confronting that misconception, I guaranteed you that most of those people would then remember that, and were surprised by it. It became something that they talked a lot about afterwards. So I think reaching to where people are, the biggest mistake teachers make is assuming people are interested in what they have to say. So you want to go to where people are, and then try and drag them to where you want them to be. Again, I don't want to spend too long. I don't want to take too much time, but that's probably my answer. I can't hear you. You've muted yourself, Prabha. You've muted yourself. You have muted yourself. We can't hear you.
Sorry, but yeah. Sorry. So what you're saying is to make a connection to what is learned in school to what happens in the
Or what
forefront
people
of
think they
science.
know. What people, yeah, to what people think
Okay.
they know, and show how powerful it can be, or how they could be wrong. Both of those things work under different circumstances.
Yeah, nice. All right. Next one, Dr. Hassan. In your experience at NASA, how do you convince or choose your global partners based on the relationship between curiosity-driven basic science and the more mission-oriented applied research evolving in space exploration?
At NASA, in the Science Mission Directorate, which is where I work, all our missions are really curiosity-driven. Whether it be biology and physics experiments conducted in the microgravity of the space station, or our telescopes, which are exploring the sun or the solar system, or our own planet Earth, or the universe, trying to learn how the first stars and galaxies were formed. And applied research, such as developing the technology of the James Webb Space Telescope, has the same scientific goals are the motivation for that applied research. So when we seek global partners, we seek for those who have the same scientific vision that we have, but they can provide complementary skills and resources to NASA so that we can achieve our mutual goals. And I would say we don't actually persuade our global partners, but we negotiate with them so that we can leverage off each other's strengths to optimally succeed in our quest for our knowledge. And I'll also add that the science data that comes out of NASA missions is made publicly available to the entire world. Anyone can pick it up, analyze it, and come to their, get out as much science as they can. People are actually using James Webb data, is even being used by artists to produce art.
That's a new one. Okay. So it's everything is basic there then. Okay. And Prof. Dawson, given your work in fostering global partnerships, what challenges or opportunities have you seen for building a sustainable ecosystem that supports long-term basic science research?
So let me speak first about the positive aspects. So the opportunities. And well, I think that this global way of communicating that we have that now is so common, that came with the pandemic basically, helps a lot this global entrepreneurship in science. And it's providing lots of opportunities for collaboration. And there are many initiatives to try to help develop regions where science is not so well developed, using remote, the internet and ways not only to talk and exchange ideas, but also UNESCO has a program for the remote control of equipment, which is targeted for scientists from Africa, so that they try to give them access to infrastructure where they can do their experiments. It's basically for material scientists and also physicists, with the collaboration of the International Union of Crystallography. That's something very interesting. Then also access to computer resources from all over the world, so that you can be in your home institution, but having access to a much better computational facility. So the way we are communicated is given us all these opportunities. The movement of open science, to share data, to share results, etc., is also something very important. Of course, for example, for open access, open access is very expensive in many places of the world, so it's not so easy. But I think that we should find ways to be able to share what we produce. So those are the opportunities, and there is I think there is a drive in the scientific community to advance in that regard to a more global word sharing openly, etc. But there are many challenges because many countries are becoming increasingly more closed. There is lots of difficulties for people from developing countries to get visas to attend conferences or do visits for research in certain countries. Visas are denied. Entry in some countries is denied as well. With other scientific unions, we signed a letter addressed to immigration officers to try to help with the processing of visas. I don't know if that will be helpful or not. It was signed by over 20 presidents of international scientific unions. But then also, for example, CERN, the nuclear research institute in Switzerland, where the Higgs boson was discovered some years ago, that was an example of a collaboration all over the world and openness. It also has some restrictions now with certain countries and based on political problems. And so all those are the challenges. And from IUPAP, we are strong believers that international collaboration is a driver for peace. And IUPAP has a long history of trying to act as a bridge between scientists, maybe from countries whose governments don't get along very well. And we try to do that, but this is a very complicated word nowadays. So I don't know how successful we have been, but those are the challenges, try to overcome those limitations.
I can understand the passion on science, on physics, being equal to everybody. And on the other hand, I also do understand the axis of evil and axis of good. How much does it really affect physics?
Well, it affects in the sense that there are people that are denied the participation in certain activities. There are two types of restrictions. One is related to political problems. For example, people with Russian affiliation. Russian was like excluded from CERN, basically. And then there are also economic motivations, like quantum science and technology is a sensitive type of science now. And so it's collaboration there is not completely open because, I mean, countries want to protect their research in that area, even if it's basic. And so we cannot be naive, but on the other hand, we think that it's very important to allow the collaboration. So it's hard to navigate those waters in which, I don't know, you want to be open, but then also understand the concerns that some countries can have. But to think that also the communities, the science communities, are willing to collaborate, actually, I think, and maybe the governments do not want to.
Yeah, I suppose it's the openness applies easily for subjects that are yet not subjects, sorry, things that are yet to be discovered. Those things
Yes.
like quantum and communication, all that out.
Yeah.
Okay, moving on. I'll pose this to Dr. Ashima. how do you communicate to the public, especially the younger generation, that even the most cutting edge space missions depend on decades of fundamental or basic scientific research?
So we recognize the importance of this question that you've just raised. And so NASA has a very vibrant education and public outreach program. And in fact, in the Science Mission Directorate, we have something called a Science Activation Program, or SciAC for short, which connects people of all ages and backgrounds with science in ways that activate their minds and promote a deeper understanding of the world and beyond. And through this program, NASA provides publicly available online resources, which are in form of lessons, lectures, and written material. And in addition to in-person public events at schools, libraries, science museum, planetarium, etc. And we also take advantage of major events such as a total solar eclipse, which happened across the United States last year. And this provides us an opportunity to engage the public in NASA science. And NASA astronauts and scientists are a big draw at big public events where they demonstrate how the technologies advances led to the space age that the younger generation now takes for granted. We saw the first man, our generation saw the first man take a step on the moon. But now it's my grandchildren's generation. This is real history to them. They just take it for granted. And in addition, we also have a citizen science program in NASA. And through this program, the public gets a first-hand experience of conducting cutting-edge science themselves. And they learn to appreciate that, as we would say, that all new discoveries are built on the shoulders of giants. And so this is our attempt of engaging everyone in the public, and particularly the young generation, to emphasize the importance of science and of building on what we already have. And I mentioned the James Webb mirror before, and that was a new technology. And we knew we had a segmented mirror at the Keck telescope in Hawaii. So we knew we could build a segmented mirror, but the idea of folding it and putting it in a rocket and then sending it to space, that was a whole new technology in itself. And, getting the lightweight material and all that good stuff.
Yeah. On that note, two additional questions. Maybe one first and one a bit open. Like what Prof. Dawson said earlier, that there is a UNESCO remote control for experiments. Is there a remote control stuff for NASA satellites?
Everything is remote control. I mean, I'm not quite sure
what I mean is remote control for people like me to do stuff.
Oh, for people like you to send signals to our telescopes.
Yeah.
I don't think we have anything like that yet, to send signals to the telescope or to the rovers on Mars or something.
Okay, all right. On another note, you said you have a lot of that NASA has this SciAct and all that. Do you see a decline in number of younger generations who are interested in science, or is there an uptick? Because here in Malaysia, we worry about number of students going into science subjects. We separate our teenagers at the age of 15, 14, 16, sorry, to other literature-based or science-based, and we see a decline in the number of science students. Do you see a decline in your SciAct programs, outreach, and all that?
Yeah, we don't in the US we don't do the kind of separation that is done in
Yeah,
Malaysia or
understood.
India
Yeah.
or several countries. Here, pretty much everyone is encouraged to do everything that
Okay.
they're interested in.
Hmm.
SciAct, we try, it's not strictly to educational institutions, but to everyone. And so our reach and we work within the United States. So our reach has been increasing, going to the number of states and the different kinds of communities where there are certain states and certain communities where very little science was taught or very little astronomy was taught. And we have been able to reach those communities with our, SciAct, because astronomy, everyone loves the sky. So astronomy is a good hook to get people to learn science. So I would say that our astronomy reach has been increasing.
Amazing. Okay.
And whether there's a generational shift, I'm not sure we've done that analysis.
All right. And Prof. Dawson, do you see something like that in your global outreach?
I don't know at the global level, actually. I can tell you about my university,
Okay. All right.
which is, and we've been increasing in recent years
Oh,
the number of physics students at the but they are not very large numbers overall if you compare with other careers. But we have a larger number than in 10 years ago. Yeah.
okay. Increasing is good. And Prof. Kraus?
What was that? I'm sorry.
On the decline of number of people coming into science.
Well, I can't comment on that particularly because I'm retired from the university. I think I will say that I suspect that there will be a decline because of what's happening in the United States. The fact that interested students are being turned away because of the lack of support from the current government, cutting back on all research basically, and also on international students who are essential to the health of science in the United States. So those developments I suspect are going to cut back on. First of all, departments will be able to support far fewer graduate students because of the cutbacks in support and NASA and the NSF and the DOE and then I suspect, as I say, that since foreign students are really a significant part of graduate education in the United States, that'll be heard as well. As long as the government suggests that foreign students are not welcome, it's going to really hurt the country, in my opinion.
Okay, that's sad actually. Hopefully, it's just a short term. Another two more years, 3 more years.
I think there's three long, hard years. Yeah. Anyway.
Okay.
I am somewhat less pessimistic. I
Okay.
think,
All right.
yeah, I think society in the United States has a great ability to rebound, and we still see a lot of interest in young people, at least in NASA science, when we take it to them. So as long as we keep the young people engaged, they are the future.
Well, of course, you're absolutely right. We got to keep the young people engaged in the future, and if they're young enough now, they'll be in a
Yes.
position later on where maybe all of this will go away. But right now, unfortunately, you're seeing a lot of. I think from what I can tell from my colleagues, there are a lot of people who are at the point of graduating as undergraduates who are seriously reconsidering whether they'll go to graduate school. Unfortunately, I hope that's a short blip. And you're right, the young people are the future, and we got to keep the young people going. And so we should be working. We should always be working with the young people because, first of all, adults are a done deal. It's too late to help them, a lot of them. But the young people are a chance to get them excited. So yeah, and that's something I tell students as well. By the way, I'm old enough that I've gone through many phases where jobs were very scarce, and students would always ask, should they go into the field because there may be no jobs? And I'd always say, first of all, that you should not worry about a job because physics is portable. You can do many different things. But more importantly, you don't know now when you're studying what the world is going to be like in 15 or 20 years. And so um, things can change. And I know when I was a graduate student, there were no jobs in my field. I remember I learned how to juggle or drive a taxi because I fully expected not to get a job. But I try and convince people that the reason to study physics or any other thing is because you love it, not because you're worried about getting a job.
Like you, when I was a student, I was a student in India and a female student.
That must have been hard.
Yeah. So I didn't think I'd get a job, but I did it because I loved it. And then
Yeah.
I did nuclear physics, and people said, nuclear physics is dying. Why do you want to do nuclear physics? I said, well, I love doing it, nuclear physics, and as long as someone pays me to do it, I'll continue to do it. Otherwise, I'll switch, which is what I did in the end.
Yeah, absolutely. And that's a nice thing. Yeah, you can always, if you're a lifelong learner, you can always switch, which is a wonderful thing.
Yeah,
And
yeah.
we have to convince people more of that. I mean, I spend a lot of time telling people, and it's absolutely true, what relates to what we've talked about earlier, that much of the physics that I now know, I didn't know when I got my PhD.
Yeah.
And that's really the important thing, is that finishing your
Yeah,
at the time when you finish learning.
I agree with
Because
you. And my late uncle used to tell me that if you do a PhD, don't think it makes you an expert in anything. It just gives you the ability to think and work independently.
Bingo.
That's basically what we said before. That is the how you approach the problems rather
Yes.
than how much you know about the object of study, I would
Yes.
say.
It's a training to do critical thinking.
Mhm.
Yes, I could relate very much to both Dr. Shima and Prof. Kraus to what you said earlier, because Malaysia is a sort of a manufacturing country, not not so heavy on basic fundamental science. So physicists are looked down over here. What we want is we want engineers to feed the manufacturing industry. So I had cold sweats. I can relate. Okay. Next question to Prof. Dawson. IUPAP plays a crucial role on fostering international collaboration. So how can emerging economies leverage these collaborations to build a stronger basic science infrastructure and avoid the brain drain effect?
Well, I think that networking is very important there. There are many initiatives worldwide for shared infrastructure, for example, and that can be copied at the regional level. For example, the European Union has a strategy for research infrastructure, so that instead of replicating in many countries the same type of infrastructure, you agree on having shared facilities. And in Latin America, there is a similar strategy, which is mainly now focused in high energy physics and also related to astrophysics. But the idea is to also expand that to other areas. Bioimaging is it's an area with a very interesting initiative. There is a global bioimaging initiative with a to share knowledge, to share data, and also to give grants for researchers from regions less developed to visit infrastructure laboratories more developed and do their experiments there. So there are efforts in community building and also in this idea of research infrastructure. And I think that in regions that are less developed, you can think regionally to try to establish this type of infrastructure, shared infrastructure and collaboration, so that you guarantee that the people don't leave the region, at least. In bioimaging, there is this global bioimaging initiative, and there is also one in Latin America, which is Latin America Bioimaging, for training and sharing facilities, etc. So one way is to try to agree within a region to make a more efficient use of the limited resources that the less developed regions have, to guarantee that the people who are trained don't leave the region. IUPAP in particular has a project together with the Union of Crystallography for community building in the use of advanced synchrotron light sources. And so we fund travel grants for it. They are called faculty students grants to visit synchrotron facilities. We have many synchrotron facilities associated with the project. And so we give these grants yearly, and we help with the community building. So those are the ways in which we can try to help with the development of the scientific communities, but at the same time helping that they can develop in their own region without contributing to the brain drain.
That's nice. I'm new to this shared infrastructure. How does it actually work? One place sets it up and the others
Well,
inject funds, or
there are different types of things because it depends on how large the infrastructure is.
yeah.
In the case of advanced light synchrotron facilities, they are large, and so it's a lot of investment. And here what we help with is with the community building and with these travel grants to go and know about the existence of these facilities, what you can do. And then those facilities, they open calls for the people who want to do experiments there. You apply, they give also grants to go and stay for a few days to do your experiment. And there is one very large one in Brazil, for example, one of these, it's called Sirius, and they have several grants for people from Latin America, but it's open for researchers from all over the world. But then for the bioimaging thing, the idea is also to share smaller equipment so that you can associate your lab with this project, and then you offer also your lab for people to go and do some experiments in your lab. So it's not limited to large infrastructure, but it's also a network in which you offer part of the time of your lab equipment for other people to come and do experiments.
So
That's
it's more
that's the basic idea.
it's
In particular, for example, in Argentina, we had many, now they are discontinued because our current government is not supporting science, but we had a bunch of national programs that was to make a more efficient use of our facilities. And there was one on microscopy, one on lasers, one on supercomputing facilities. So many of those, when it's large infrastructures, usually they have some time allocation that is open for people that want to, to run their programs there. But so you have to submit a project, the project is evaluated, and then if it's very good, they give you time. And in this very same way that they give you time on a computing facility, you can have time in other types of facilities. Yeah.
so it's more of a local setup, local initiative instead of a large national initiative.
Yes, it's a network. It's a network in which
Okay.
everybody is trying to help one another.
Okay, all right, understood. Prof. Kraus, your work often explores the philosophical implications of fundamental physics. How do you reconcile the pursuit of knowledge for its own sake with the increasing pressure to demonstrate immediate practical benefits in research funding?
Well, I think there's a few ways. First of all, I think once again, it's just a matter of convincing people that you don't have to convince people. People really like the wow stuff, the fundamental stuff, the nature of cosmology, the Big Bang, the energy of empty space. I often say, I point out that I'm really quite proud of the fact that nothing I've ever done has any practical application whatsoever, and that's okay. I think, having said that, one has to. What I also talk about is that curiosity-driven research has changed the world. One never knows what the applications will be. While I'm absolutely certain, well, I'm not certain. Well, I'm strongly of the opinion that nothing I've ever done will ever have any practical significance. I don't know for certain. And one can say that in many cases that's people have been wrong. If people in what I like to point out is if people in the 1940s or early 50s had been asked to build a better computer at Bell Labs, they would have been making a computer with wheels and turns and cranks. But when someone invented the transistor, it changed everything. When fundamental research involved in penicillin, when fundamental research at the Large Hadron Collider, what was then before the Large Hadron Collider, but at CERN, the laboratory where basic physics or fundamental physics of particles is explored. Well, when 5,000 physicists wanted to communicate over a medium where it didn't depend where people were or which computer you were working from, they developed what is now the internet. One can go on with many similar examples of fundamental work. I'll give you a good example. An old colleague of mine when I was at Harvard, Ed Purcell, who was a wonderful physicist, Nobel Prize winner, and a lovely man, who developed nuclear magnetic resonance. That's what he won the Nobel Prize for. But when he was asked about that, I remember if you read interviews around the time of the Nobel Prize, he said, this is a fascinating phenomenon, but it really won't ever have any practical use. But of course, NMR is fundamental in medicine now. So I think one can say that that curiosity-driven research has ultimate spin-offs, but I don't think that you should justify anything based on the spin-offs. You should justify it because the ideas are important. And what I like to do, in fact, I just wrote this in a piece that just appeared. I love to quote Robert Wilson, the first director of the Fermi National Accelerator Laboratory, another particle physics accelerator laboratory in the United States. And when that was being built, he had to testify before Congress, and he asked if it would aid in the defense of the nation. And his answer was no, but it'll help keep the nation worth defending. And I think that's a key. I think I'll let his last words be my last words on this question. You're muted again.
You can't argue with that. If you put it, I'm okay. Yeah.
Okay.
Yeah. You can't argue defending. Yeah.
Okay.
That's a good
You
one.
cut out there. I didn't hear everything you said, but.
No. What I mean, what I said was the part that it's worth defending. That's
yeah, absolutely. Because that's the point. These ideas are part of what makes people. They're questions that everyone asks. Where did we come from? How did the universe? Are we alone in the universe? These fundamental questions that are really central to modern physics. same questions everyone has. And um, and what I often say also in regard to this is that one of the I was going to say one of the sad pieces of science, but not really sad piece. Um, the fact that science begets technology is wonderful. Of course, it's changed the world, but it's also, in some sense, a curse because people don't ask what's the value of a Picasso painting or a Mozart concerto, um, because it doesn't produce technology. But the ideas of science are the same. They're the beautiful. They're the peaks of human intellectual activity. But too many people think because science begets technology, that's all science is good for. But in my opinion, it's the ideas of science that have changed our perspective of ourselves that are at least as important as the technology, if not more important.
That's a that's deep. That's a new insight for me. That
Good.
that it,
Well,
it's as
then my
beautiful
work is
as
done.
art. Yeah,
Okay,
it's
good.
as beautiful as art. Yeah, correct. That is a new way of looking at it. Yeah, that's a good one. Nice.
Good.
Thanks.
Well,
You made
thank
my day. All right. The Prof. Dawson. As global physics increasingly becomes interdisciplinary, how can basic physics research help inform or even lead the way in addressing challenges in other fields, climate modeling, or in your field, biological systems?
I like to talk about a dialogue rather than leading, I think,
Okay.
because different disciplines have different cultures, and I think it's important to like respect those different cultures. Not only respect, but also it's important to achieve the goal of trying to solve problems, because you need that diversity of viewpoints to advance. Lawrence, I mean, Professor Krauss, he mentioned
Lawrence is
something
fine.
about climate change and physics. And let me tell you that last year we had our General Assembly, and Giorgio Parisi, a Nobel Prize laureate in physics, he gave a very beautiful talk about physics for sustainable development. And he was talking about many things that we still don't know, basic things that are related to basic physics, which are related to being able to predict better changes in to predict better the weather in particular, but also what he called the tipping points, extreme events. And for that, you need a basic understanding of the processes that are underlying the observation. Some years ago, in 2022, we had the celebration of the IUPAC centenary, and there another physicist who works on problems related to climate modeling, Tim Palmer from Oxford, he mentioned that there is a need to have more people developing new models to models of the atmosphere, and also the coupling between the atmosphere and the ocean. And he was suggesting that maybe something that IUPAC could help with is to promote that people who did their PhDs in whichever areas of physics would like to switch, as Professor Hassan did, into the area of climate modeling. So, because it's important to bring this way of looking at things and what we call understanding, which is something that is being challenged now with the use of machine learning and AI, what it means to understand something. And I think that when you have this physics training, you have a particular way of thinking what it means to understand. And that's very important, in particular, to predict things that you haven't observed yet, because you need to develop models to be able to predict things that you haven't observed yet. in biology, there are many contributions that physics does. On one hand, is developing of new techniques that allow the observation of living systems, the dynamics of living systems at work in vivo. And some years ago, it was in chemistry, the Nobel Prize, but it was awarded to at least one of the people was a physicist, super resolution techniques to be able to observe how the processes occur inside cells, and that allows you to understand better how living systems work. And of course, physics has been involved in many breakthroughs in biology, particularly the structure of DNA. And of course, I also think that modeling is very important. And there is this interdisciplinary research between physicists and also biologists that try to make more quantitative predictions. Of course, living systems are much more complicated, but sometimes physicists try to reduce the descriptions too much, and biologists try to keep all the diversity. But I think that through that dialogue that seeks the correct balance to be able to make some predictions using some modeling and looking at the diversity and the variability of the observations, you are able to do many things in biology with the perspective of a physicist.
How much of all those stuff in quantum comes into biology?
Well, there is quantum biology now. There are some processes, I don't know, photosynthesis and also electron transfer, which are basically quantum. But there are people doing research in quantum biology. I don't know exactly what they do, and there are other people that are trying to look at, I don't know, whether the entanglement of photons affect a vision, or looking into things that nobody thought of before. So I don't know how much they are producing, but there is a movement there. Yes.
Yeah. Okay. Including I think a good example. I'm not sure. I think I saw it in YouTube that they were using lasers to kill cancer cells. So there's some photon interaction there. I don't know how it works, but I suppose so. This is one field we could look into.
Mm-hmm.
Okay. Dr. No, yeah, Prof. Ross. In your view, how can we better integrate the historical lessons of basic scientific revolutions into our modern research agendas to ensure we're not missing the next major leap forward? I think you did answer a bit of it earlier.
Well, no, I think there's some additional things to say there, though. No, I think first of all, we don't know where the next big breakthrough is going to come from, and people always ask me what's the next big thing, and I always say if I knew, I'd be working on it. But so I think that's very important. It's the big surprises are surprises. But what I think we need to do is ensure that we allow the best people to continue to do what interests them, precisely because we don't know where the breakthroughs will occur. And I'm particularly concerned when with developments that are changing that. We need to make sure the best young people are not turned away from science or from fields because of in the United States, because of their gender or any other reason. And we also have to ensure that while of course there's important applied research that needs to be done, that the breakthroughs are going to come. Most of the breakthroughs, in any case, not all of them, but most of the breakthroughs are going to come from letting people who are talented work on what interests them, and and then just let 1,000 flowers bloom. So I think we need to point out that you take any of the major developments that were in science, that they were in many cases unexpected. They came from unexpected areas of research, and that's true beyond just physics. That people weren't looking for what they found, and from Isaac Newton on, when Isaac Newton was happily away from the university because of a plague, he was able to sit. It's probably an apocryphal story, but he was still able to sit in the field and have an apple seem to spark his imagination. And there's so many examples of that. So I think what we just have to say is that we have to ensure that we always ensure that merit is the essential factor in hiring and promotion of people first, and secondly, that what we do is we hire good people and we say do good things, and and that's going to produce a wide variety of things, but some good, some bad. But since you don't know in advance always where the next breakthrough is going to come, you have to be willing to gamble on people, on intelligent people, and hope for the best. You're muted again. It seems every time I talk, you mute yourself. But I'm sorry.
there's some kind of network entanglement there.
That's right. I'm scaring your computer, I guess. I'm sorry.
Yeah, I suppose so. What I said was that's a big gamble there, gambling on people.
Well, I think it's life is the future is a gamble, and that terrifies some people. The future is terrifying, but it's also exciting, and the only way we'll find out is by marching bravely into it.
Oh, marching bravely into it. That's. Is it really that dark that we have to march bravely into it, or in that sense it's a quantum leap, right?
Well, I never
otherwise
understood
it's just
by the
going to
way, I hate the term quantum leap because quantum leaps are very small. People always use the term, but they're
okay.
so
All
it's
right.
an exactly wrong nomenclature. But I think you have to be you have to be brave enough
we did argue on this earlier. Yeah.
Ultimately, I don't, by the way, I don't think academics are particularly brave people in general, but intellectually, you have to be willing to be brave enough to follow what you're interested in, and that means sometimes working against fads and other things, and being courageous enough to be wrong. That's the other thing, because what most people may not realize is that if you're a researcher, most of the time, you're wrong. You're not necessarily making mistakes. It's not as if they're mathematical errors, but many times, if you're a theoretical physicist like me, if you're a theoretical physicist like me, you often discover that nature, for some absurd reason, doesn't seem to agree with the things that you're proposing, and in spite of how beautiful they may seem to you, or to me. So I think you have to be willing to be wrong a lot of the time, and that also takes some kind of courage. So yeah, but everything from AI onward, the future is both terrifying and exciting. And I think that's what makes life so interesting.
Nice. So I correct myself, not quantum leap, warp jump.
Warp drive, jump, warp jump. Well, thank you. That relates to my book on the physics of Star Trek. So I like it.
Okay, Dr. Hashima, how much basic science has gone into both, or not just both, any of the big things that NASA has launched, Hubble, Sophia, JWST, what else? A lot of things. And is this the basic science actually reflected in the type of data obtained from such projects?
Yes, absolutely. Basic science underpins all our flight missions for space science, whether it be testing Einstein's theory of general relativity with Gravity Probe B, or the missions you've just mentioned, the iconic Hubble and JWST. And the way we do it, the US Academies of Science, Engineering, and Medicine convenes a committee of community experts every 10 years to identify the highest priority science that should be undertaken by NASA, the National Science Foundation, NSF, and the Department of Energy in the following 10 years. And this expert committee solicits ideas from the community through white papers, which it incorporates into its final report, which in the case of astrophysics is called the Decadal Survey for Astronomy and Astrophysics. And NASA then plans the highest priority missions such as Hubble, Chandra, JWST, and its follow-on under construction that I mentioned earlier, the Nancy Grace Roman Telescope, based on the decadal report. And the basic science to be conducted by the mission directly influences the type of data which is sought to achieve the major scientific goals, and hence the required technology. For example, the scientific goals for James Webb to view the first stars and galaxies, study the atmospheres of exoplanets, learn about the outer planets of our own solar system, and to seek the elements which formed life itself. To learn about all that, it determined the wavelength that was required, which goes from near infrared to mid infrared, and also the nature of the instruments, both imaging, cameras, and spectroscopy. So that definitely determines what kind of data has to be collected and the science instruments that have to be made, and hence the mission architecture.
So it's all basic science.
Yes.
And what about the data? Data is considered basic science, or is considered something else?
Well, the data is, as I mentioned earlier, the basic science is derived from the data. So we put all the data in our archives, and the scientists anywhere in the world can pull up whichever data they want to extract the science that they are interested in. So the James Webb data, they're interested, they see some galaxies out there, they want to learn more about it, they extract the data from the archives and they analyze it, and they come out with the results. And it's the same with all our missions, whether they be Earth science data or planetary science or solar physics or biology or astrophysics.
So every
the data
10 years.
itself is in the basic science, but you extract the basic science from the data.
So every 10 years, these guys meet and an idea is formed, and from there the technology is built up.
That's correct.
Okay, so let's say for example, today we decide that this something is important to be looked into by NASA. How long does it take from today to actual seeing the data come back?
So typically, the what we call our flagship missions, like Hubble and James Webb, it's taken from the day the Academy report came out, and we started working on it, about, I would say, about 20 to 25 years, because James Webb came out from the 2010, and it was launched in 2022, and the data came out in 2023. So actually, that was less than 20 years. No, it was the 2000. Yeah, it was the 2000.
But to be fair, John Mather, who's a good friend of mine, would say that James Webb, the work on James Webb, the thinking about James Webb actually began at least a decade or two before 2010.
Yes.
Yeah, and
So, in
I
fact,
think it's
I sent the first grant from NASA headquarters to John Mather in 1995.
okay, so there you go. Yeah, so we're
And, and,
from the time it
and,
was
direct- and directed him to think about the next generation space telescope.
So,
Yes.
yeah, Vic, we talked about it on my podcast with him, but yeah, absolutely. So there's a good 20 years there. But it's also worth pointing out, you're absolutely right. It's can be 20 to 30 years, sometimes longer. But it's also, I think, worth pointing out that these are recommendations that are made,
That's
but that doesn't mean the government adopts them. And so, you know, the recommendations by the National Academy, and the government could choose to follow them or not. And one is subject then, of course, to the vicissitudes of politics.
Yes, it's a long process, and since this is a taxpayer-funded project, we have to take it to Congress, and then the Congress has to approve the funding, which may or may not be sufficient, and so it's a very lengthy process.
Well, in fact, as you know, and at many stages, I just think it's worth pointing out that this is a precarious and difficult activity, and scientists commit their time and effort to projects that may take decades and sometimes may not happen, because I just remember vividly writing Congress on for John and others to try and save the James Webb Telescope at a time it was going to be killed, and then another time in my other field of elementary particle physics, trying to get Congress to continue to build the superconducting super collider, which would have discovered the Higgs a decade or two before it was discovered at CERN, and that was canceled. So this is precarious, and it's by no means guaranteed. Means it's not really guaranteed, but scientists have to continue to work on it, and we owe it to the public to convince them that these are important things, because as you pointed out, these are taxpayer funded projects, and so an important part of science, and NASA does this perhaps better than any of the other, I think probably better than any of the other science agencies, in convincing the public that what it's doing is of interest. But I think scientists have to spend more time realizing, and many have, that the public is going to fund these things, and therefore we have to convince them we can't just rest on our laurels. As physicists and as a nuclear physicist, you know this, after the Manhattan Project, for a long time, physics cruised along, knowing that the government would continue to support physics because we'd done something big. But those days are over now. I think we have to realize that if we're gonna get the public to spend money on science, we have to do a good job of trying to explain to them why it's important.
Yeah, and I mentioned the decadal survey, which involves not just the initial committee, but the committee solicits papers from the entire scientific community of their ideas, which come in white papers. So really thousands of scientists contribute to this decadal survey. So it is a total community effort, and that is why it gets the support of the public and the taxpayer. And
But also sometimes the questions, I mean, scientists know what questions they want to answer, but they don't know with which technology they have to develop the technology. Like, for example, CERN now is discussing a new collider, which is called the Future Circular Collider. And if you go to the page of CERN, you see that they expect that they will be able, I mean, if everybody approves because it's a lot of money, etc., etc., They will start the construction in 2030 and be able to measure the kind of collisions that they are interested in 2070, because they have to find the technologies to be able to do that. So it's a long time. And I was thinking also of LIGO, the observatories of gravitational waves, that also started as a sort of proof of concept many years before they were able to develop the technology. And in doing that, you develop new things. You have a lot of positive side effects, because all these technologies serve for other purposes as well. But when you start, you don't know exactly how you're going to be able to solve the problem of observing what you want to observe. So that can take a very long time. And it's the motivating question is basic, is you want to understand how nature works at different scales. And in doing that, in order to be able to observe with the level of precision that you need to answer the questions, the basic questions that you're asking, you need to develop new technologies, and that's completely open.
Yeah,
That's a
exactly. You have to be brave.
point.
I'll just jump in. I mean, I was, as a theorist, and many of my friends were working on LIGO and to help develop LIGO. But I never really thought they'd be able to do what they said
Yeah,
they'd be
well,
able to
I
do.
still don't understand how they are able to to measure those
It's
different.
amazing, but I was highly suspicious.
I can't believe it. I have very good
it-
friend Gabriela Gonzalez, who was the spokesperson when they observed the gravitational waves, and I still don't know those. I mean,
Well,
those
it's
numbers are
remarkable,
amazing.
but they had to just keep plugging away, and through many stages when they weren't getting there, hard work, baby steps
Yeah.
over a
And
long time.
there was a lot of work also, data analysis,
Of course,
and so
you have to know it was a beautiful thing because the experiments required new technologies, but so did the theory, because you have to compare the signal to something's predicted, but no one knew how to accurately predict the signal. That required developments too. And so that's the kind of bravery I was talking about earlier. You've got to be willing to go into the unknown without knowing if you're even able to do what you want to do. So it's
Yeah, and that's
so
and
you have
sometimes you fail.
yeah,
you
and
have
that's
it.
an excellent point. Whenever I give science talks on James Webb, I say that, the scientists dreamed these great dreams, but it was the engineers who made the magic happen, thinking of
Yeah, I'm in
how
awe of engineers. That's true. Yeah.
yeah, I mean, the engineers and scientists working together, but designing this mirror, the sun shield, because you know that you can't put such a big telescope inside a rocket. So how do you keep it cold from the sun? Okay, let's put an umbrella under it, a sun shield, and that was a whole new technology in itself, and as well as the
Yeah.
science.
And you develop that as you advance with the project, because you cannot know everything ahead of time.
Yeah, I
So
remember the very first technology workshop that we attended. Oh, I know, don't remember. It was in the late 90s, when they were showing these mirrors and opening mirrors, and they were just PowerPoint presentations at that point, and we asked how much would they cost, and they said we have no idea. And at that time, they thought they could build the whole telescope for $500 million, and we ended up paying 10 billion. So.
oh my goodness.
Which used to be a lot of money, by the way. 10 billion used to be a lot of money in the old days. Anyway.
And it's not now?
Well, I mean, you see, you see 10 billion being spent here and there on many things.
Yeah.
On that, so it's yeah. Anyway, that was just it's true. $10 billion was a lot of money, but now you see that it doesn't seem like so much, in spite of the fact that actually it's more than the budget of the entire National Science Foundation. So it depends where you are. In some places it's nothing, and in other places it's a lot. And fortunately, people don't realize that $10 billion funds more than the National Science Foundation, but $10 billion is what you pay for a software company nowadays. I mean, it's really in the grand scheme of things, and in terms of the budget of the country, it's actually very little money when you think about it. And
We
that's
did $10 billion over 20 years. It wasn't
Yeah,
a
Over
money.
20 years,
main thing, yeah.
exactly.
It's not
Exactly.
constant. It's not constant. It's
I unfortunately say
cyclical.
I hate to say this, but I'm going to have to go in a minute. It's kind of late here, and I'm
Yeah,
I'm
yeah, yeah. I understand.
up at my
Understand.
house, and so I have to go in a minute, probably
Okay.
by
Okay.
11.
Let me give you one last open question, and then we'll go for other questions and maybe pictures. Oh, sorry. Especially this one for you, Prof. Kraus. Some critics argue that basic science is a luxury for wealthy nations. Do you believe developing countries should prioritize on it, and why?
Well, I think it is a luxury. I mean, basic science is a luxury, and of course it wasn't able to be done until you have to, if you're worrying about feeding yourself or having lights at night, it's hard to imagine doing those luxuries. But on the other hand, one of the important lessons I think that can be learned is that if you want to excite young people who are then going to help the economies of their country, if you support the most exciting ideas, and some of them aren't expensive, like some theoretical physics ideas, you attract people who are then going to go on and do other things. I remember, for example, speaking of India, I've spoken years ago at the IIT in India a number of times, and I see the excitement that all of these young people have when I talk about the universe, even though none of them they're all studying to be engineers, but you can use the fundamental science as a hook to excite young people who will then go on to develop the technologies that are necessary for developing countries to raise their standard of living. So I don't think it's an either or. Sure, you can't build an accelerator, but you can support people working on some forefront ideas because you'll attract the best young people in your country to want to be educated, and that will inevitably help the economy of that country, I think. So, but it is a luxury at some level, and I'm not going to deny it. And but once again, you don't have to break the bank to be able to make an impact. And even in mathematics, for example, there are lots of areas that don't cost a lot of money where you can focus some fundamental research, and some of it is now in genomics, and some of it maybe now in AI. And so there's you have to be strategic about it, but I can't I don't think any of the young people who've later on gone to become major technologists or entrepreneurs, I suspect every single one of them was inspired at some early stage of their life by something fundamental and profound. And so I think it's important for countries to realize that.
So what you're saying is basic science is a luxury, but we don't have to go the full like what you say, a full collider or full LIGO, but parts of the science that support it.
Well, there can be fundamental science that is expensive, and the other thing that's important is, especially when it comes to big projects nowadays, they're almost beyond the ability of any one country anyway.
Yes.
And so it's possible for countries, and at CERN, there are many countries involved, and there have been who don't have a lot of money, but they can become partners in large international collaborations. And it's great because it trains the young people who go to CERN or go to work or go to NASA or wherever. They can get trained and take those techniques back to their country. So getting involved in large international collaborations, if they're done right, is a wonderful thing for some less developed countries. They don't have to take the lead, but they can help train young people who later on will take the lead in something else.
Okay. One question on to all three of you, but especially Prof. Kraus, before you leave. What advice would you give to young scientists and students who are passionate about fundamental research but feel the pressure to focus on more immediately marketable or applied ideas?
My advice to them is, you're not going to be any good if you do something you're not interested in. And so you should follow your interests. and you never know where they're going to lead. And you shouldn't worry about where the jobs are, because as I said earlier, in 10 or 20 years, the jobs could be somewhere else. If you're pressured to work in an area that you don't find in your heart excites you, you're never going to excel at it anyway. So follow your dreams. And the other thing I always tell young people is don't let the bastards get you down.
All right. Okay. If you would like to leave now,
I have to, and I'm sorry. It's been a
Yeah.
pleasure, and I'm sorry I have to go.
we'll take a picture with everybody, and then you can leave.
Okay.
Guys, online, you can switch on your cameras, please. We'll before we wish good night to Prof. Kraus.
Well, it's nice to see all the faces.
Yep.
It's very heartening.
They are alive. It's alive.
Well, yeah. While waiting, I should thank my colleagues on the panel who I enjoyed listening to, and congratulate them for the good work they're doing.
Likewise.
Efforts. So I appreciate it.
All right. Shah, pictures.
Picture almost there, complete now. There we
Okay.
got almost everyone.
All right.
Okay.
Okay. Shah, okay.
Good.
All done.
Let's go.
Okay. All right. All right. Thanks. Good night,
Bye.
Prof. Kraus. Some other time then. Okay. Bye. Have a nice night. Ciao.
Yeah, thank you.
Thanks for joining us.
Sure.
Bye.
Bye-bye.
Okay. And Prof. Dawson and Dr. Shima, I would like to go back to what you guys said. It takes 20, 25 years to get a proper project out, NASA or even CERN for 2070 measurement. How do you decide when to stop? What I mean is you're cruising along 10 years and 20 years down the line, suddenly you say, oh, there's some new technology that could do this better. Do you throw the old one away and bring the new one in, or just chug along with whatever you have? How do you know when to stop?
I will tell you that the technology in Hubble Space Telescope is from the 1970s.
Wow.
Okay. So, no, you can't throw away technology and start all over again. You can adapt. With Hubble, we were lucky in many ways because it was designed to be serviceable. So we sent up 5 servicing missions where a lot of, failed technology was changed out. The science instruments were changed out. But the computers over there are still the 1970s computers. You couldn't change those out. So
Is that a computer or a calculator?
well, they call them computers those days.
Okay.
Yeah, I don't know. I don't have that much experience in that, but for example, this synchrotron life facility that I talked about that is based in Brazil.
Yeah.
I mean, it's a huge investment, and Brazil is a developing country, basically.
Yeah.
It's a large economy, but it's not a developed country. So when they were discussing the construction, there were already facilities in the world with established technology, but they decided to move to something that was being developed. So they took it from papers, which is the type of facility they built, because they felt they didn't want to then lag behind after all that investment, which is so huge in a developing country, because it's not like, I don't know, it's not like the center of Europe that you are doing that. But they decided to take the risk of trying to put in their facility a technology that was not still available in any other facility. It was only in the papers where the other technology was being developed. That's a hard decision, But I mean, especially for a developing country, because you know how difficult that is in our.
Why did Brazil want to go into synchrotron? If you don't mind me asking.
They had a smaller, already a smaller facility, and synchrotron is something that you use to analyze lots of different materials. So it has a lot of applications in industry. You can
Yeah.
observe. So it also, and on the other hand,
Medicine.
it had a lot of, I mean, a huge impact in the economy because it led to the development of new companies to produce uh, equipment that was necessary for the synchrotron light facility.
Oh,
They,
so
and
it's the whole.
it's the change. It's the
Okay.
change.
Okay.
Because in Argentina too, when there is a company that was born out of the Atomic Energy Commission in Argentina that produces reactors and also radars and stuff. And so in order to advance with that, other companies need to be set up as to be providers of part of the equipment. And so it has a multiplicative effect in the economy of the country, which is very important. And Brazil already had a smaller facility and went for this very large, which is one of the 4 of that type that exist in the world. So it was very good for them to choose the technology that had not been implemented yet in any other of these facilities. And something interesting that the director of this facility told me, which is interesting, is that the civil engineering work that had to be done, because you need something very stable for over very large distances, and that it was very important that the football world championship took place in Brazil in 2016, because they had all these constructor companies that had the expertise to build the just the basis for the construction of the synchrotron. That was a funny thing, I thought.
Hmm.
The football was important too.
The 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 feed the extension of the technology into other fields.
Mm-hmm.
Yeah.
Mm-hmm.
Okay. There is a question on the chat. I think
Mm-hmm.
I asked to ask them to you. In Malaysia, there seems to be a declining interest in pure science and mathematics among students and the public. There's a growing focus on applied and technical education, such as TVET, which may be contributing to a shortage of talent in fundamental or basic scientific fields. Many of our scientists thrive only after moving abroad, such as to the US. Do you have any thoughts or advice on how we can restore interest in basic science and support scientific talent development locally? Either one of you?
Yeah, well, I think that outreach is very important. And so, and also it's very important how you teach science in high school and so that you attract students into basic science. And there was a previous question about many of the technologies of AI rely.
Yeah.
So that also informing about that, because informing that with with training in basic sciences, then you can also then work on more applied types of jobs with a different way of approaching the problems, which I think is broader. And also basic sciences has a huge impact on education, I would say. And but I don't know how you change the culture, because it's a cultural problem, plus the I guess it's the also the desire to earn more money, and so you see that they are
How is
better
it in
paid.
How is it in
in
Brazil?
how is it in Brazil?
Yeah.
I don't know if I know that much. I've been here for a few months. I am on sabbatical for 1 year. But yes, well, I don't know how many people study science here in Brazil. In Argentina, most people study other careers outside STEM, basically.
Oh, okay. Why Argentina goes that way?
Oh, no. Well, in Argentina, universities are the most prestigious ones are public.
Yeah.
You don't have to pay to study there. And basically, students study whatever they want. There are some incentives like scholarships for the study of STEM areas. There were in the past. But there are not limits on how many students can study a particular career. There is no limit on the number, at least in my university, there is no limit in the number of students that can start a given career. So there is no policy there. It's just the demand of the students. And that goes with I don't know, what is more or less fashionable depending on times. Now data science attracts a lot of students, but a lot means within the moderate numbers that we have, which are incomparable with other careers that are not STEM.
Okay. So non-STEM is still more attractive than STEM.
Well, yeah, economics, law,
Yeah.
medicine. Medicine, it's
Medicine
very
doesn't
large.
fall under STEM?
Pardon me?
Medicine doesn't fall under STEM?
Yes, medicine goes into, well, STEM, I don't know. It's like VM is mathematics, but yeah, it could go into understand.
Yeah.
So medicine is large.
Medicine is large, yeah.
Yeah.
Even here, medicine is the number one. Law and engineering is number two. Physics is maybe 99 or 100.
But then a basic science is very important for medicine. We've seen that during the pandemic with the development of the vaccines with a new technology that was based on these RNA vaccines, and that started from more basic type of research, I think.
So you're on mute, Dr. Prabha.
Sorry, just noticed that. Thanks. Last question to both of you. Looking ahead, how do you see the relationship between basic science and major societal challenges, climate change, energy security, global health, that's going to shape the scientific agenda for the coming decades? Dr. Shima?
I would say there's always a struggle between the implications of scientific predictions and the cost of developing and implementing economically feasible solutions. And every nation may not have the resources or even the political will to take an economic risk to prepare, for example, for the dire predictions of climate change. However, I find it encouraging that by sharing global data and scientific conclusions, national leaders are willing to take steps to control the impact of climate change and of energy security and public health. And we saw a unified global response to the COVID epidemic, which resulted in quenching it. So I'm basically an optimistic person. So I do recognize the realities that the realities of life may push these scientific predictions into the background. But I think on the whole, we have managed to educate the public and our politicians sufficiently that they are beginning to take action, or definitely, hopefully, will take action before something horrible happens. And you're on mute again, Dr. Prabha.
Yeah. Sorry. No, I was talking something else over here. Uh, no issues. I understand what you said. And any thoughts from you, Prof. Dawson?
Well, of course, the role of science is very important to advance, try to solve all these problems. But I think that in many cases, the bottleneck is policy makers' decision to implement new policies. Like, for example, the problem of hunger. The world produces more food, to feed all the people that live on Earth. However, there are people that don't know if they are going to eat the following day. And that's not a problem related to science. It's a problem, it's a political problem and an economic problem. So science can do its job, but policymakers and decision makers have to do their job as well, because I think that some of the largest bottlenecks are there rather than in science development.
So IUPAP needs to have classes for politicians.
Yeah,
on
yes.
basic science.
Yes.
Yeah, that's a sad thing. The politics is actually a big bottleneck, stumbling block, a big wall actually to a lot of things. There's a question on the chat box. With the development of new technologies, particularly in computer technologies, with big companies such as Nvidia, Microsoft, and Google creating advancements in quantum computing, how would it revolutionize how scientists approach their research? Would it help in simulating data, or is it still better to do real experiment with real apparatus?
Well, computers have helped science research for many years now, but has not replaced. Computer simulation is something that is being used, but it has not replaced experiments. Now, with AI and also complementing machine learning with quantum computers, you can, for example, I was attended several talks talking about finding out molecules that could have some medicinal effects or something. And so instead of going blind to the lab to do experiments, you do your search in the computationally with the use of AI and maybe complemented with quantum computing. And then you go to the lab with an informed with more information where to look at for potential molecules with potential medicinal applications. And so it's a combination of both. It doesn't replace. I think it boosts the advancement.
Yeah.
It's an additional tool. It's an additional research tool.
How much of AI or machine learning is incorporated in James Webb?
I think at the time that James Webb was built and launched, AI wasn't really
Not strong, not very strong. Yeah, understood.
it wasn't that far along. But when we get research proposals from scientists for the observations that they're going to make, so far we don't think they have been using AI. But as Dr. Dawson has mentioned, it is a good tool for a starting point of, writing a research proposal. Get some.
ChatGPT. But but
Get
also,
AI to
when you generate so much data, you can
Yeah.
use algorithms to dig into those data and looking for regularities and eventually infer some behaviors for clustering your data, classifying your data. So whenever you generate a lot of data, machine learning tools are very useful for their analysis.
Yeah.
Yeah, I remember reading about this um, cheese company. I'm not sure where is it based, US or somewhere out Europe. I'm not sure. They fed their traditional cheese taste and chemical and chemistries into AI and asked it to come up with new recipes for new cheese. And after that, they implemented it, and apparently it's a big hit with their sales with new cheese tastes.
Yeah, I saw some application for wine actually to define a wine descriptors using
There you
AI.
go. So AI in everything.
Yeah.
It's not just yeah, at the end of the day, it still comes back to hardware to actually test it out. Okay, I think that's about thing. Thank you both
Okay.
for a good discussion. We had good insight from all of you. Thank you, Dr. Dawson, for the link to the
Okay.
synchrotron. We
No,
saw
I
that.
gave other links before.
Yeah.
Many links.
Yeah.
And Dr. Prabha,
Yes.
I should have mentioned that for my education and outreach, it's a team effort at NASA headquarters, and I'm really excited that this year we've hired a new person in astrophysics, Dr. Mia Bovell, and it's really fun for me to have someone young and enthusiastic and really excited about this work to help us take NASA science to the public and to schools and students. So I wanted to acknowledge her as well.
Okay. All right. May I get her name again, please?
It's Mia Bovell, MIA,
Yep.
capital BOVILL.
Okay. Mia Bovell. All right.
She's a young scientist who's just joined NASA headquarters.
Okay.
Yeah.
All right.
Okay.
Maybe we'll hook her on then some other time.
Yeah.
Okay. All right. Thank you. Good
Thank
night to both
you.
of you. And another photo session, probably. Another photo
Okay.
session, please. Guys, one last one for the night, for the morning over here.
I am a little jet lagged because I arrived from Europe today.
Okay.
So
All right. Okay.
for me, it's
For me,
very
the
late.
jet lag is in the positive direction because I came from California, so I'm still very awake.
Oh, no.
Okay. All right. Okay. Thank you, guys. Thanks for
Okay, thank
attending.
you.
And thanks, Dr. Shima and Prof. Dawson for joining us. Hope you keep on joining us for other Isaac series, the coming series. We will send you all the links. Hope you can join us and listen to what the other guys say. Okay.
Thank
Thank you.
you.
Good night. Good night. Bye.
Bye-bye.
Thank you very much. Bye bye.
Bye.